Trigonometry is one of my favorite branches of math, and I think the reason why is there's so many neat applications in the real world, from navigation to motion of a ball thrown in the air to circular motion of a Ferris wheel to measuring heights of tall structures, and perhaps most importantly, making sure the stairs in your house are safe enough to minimize your risk of falling. Trigonometry is all about using right triangles to calculate certain measurements that otherwise would be difficult to do. For example, heights of flagpoles, heights of sailboats, trees, mountains, buildings, lengths of ladders, how high a kite is flying, heights of houses, altitudes of airplanes and hot air balloons. Before getting into trigonometry, though, let's review what triangles are. Triangles are three-sided shapes with three angles, and they can be labeled based on the measures of their sides and their angles. When we have this situation, we can label this triangle as equilateral. The sides are equal in this triangle. If all the angles of a triangle were equal, we'd have an equiangular triangle. This triangle is an isosceles triangle because two of the sides are equal. If one of the angles of a triangle is 90 degrees, we call this a right triangle because it has a right angle. If one of the angles is larger than 90 degrees, we have an obtuse triangle. If all the angles are less than 90 degrees, that would be an acute triangle. And also, if all the sides were different, you'd have a scalene triangle. Triangles have area. If we clone the right triangle here at the bottom and rotate it 180 degrees, we can put the two pieces together along the hypotenuse and create a rectangle. Recall that the area of a rectangle is length times width, and therefore area of the triangle would be 1/2 of the length times the width. Therefore, the area of a triangle is 1/2 the base times the height. We can clone the isosceles triangle and rotate it 180 degrees and form a parallelogram. Half of the parallelogram would be the triangle. The area of the triangle then is also 1/2 times the base times the height. Cloning the obtuse triangle and rotating it 180 degrees, we get two identical triangles that can be brought together to form a parallelogram. The area of an obtuse triangle is also 1/2 the base times the height. Triangles are often not drawn to scale, so when you're given a problem and the angle doesn't seem quite right based on the diagram or the length of the side isn't quite right, don't worry about it. Just make sure that you follow the measurements given. We always label triangles using capital letters. This triangle would be called triangle ABC or BCA or CAB. The order doesn't matter. We can label the angles of a triangle a few different ways, either by using capital letters, Greek letters, or three capital letters. Angle CAB or angle BAC refers to angle A. You put the angle in the middle. Angle C would be angle ACB or angle BCA. Again, the middle letter refers to the angle. We can also label angles with Greek letters. We could use theta, alpha, or beta, but also gamma. We use small letters to label the sides of a triangle. If we have triangle ABC, the corresponding sides would be C, B, and A. Across from capital A would be little a, and across from capital B would be little b, and across from capital C would be little c. Labeling the base and the height of a triangle can be a little bit tricky, but if you think about the base and the height forming a 90-degree angle, that might help you out a bit. The triangles that are right triangles are the easiest to figure out where the base and the height are, because you have that 90-degree angle already. The next easiest triangle to label base and height probably is the isosceles triangle. When two of the sides are the same, the height forms from this point down, because that would make a 90-degree angle. This triangle might trick you a bit, but if you put the base here, you can extend the height down to meet that base. The height of the triangle here would be in red, and the base would be just the blue line. And same thing for this one. If you label the base in blue, you can extend a line down to the base to form that 90-degree angle. Sometimes you have to imagine the triangle rotating so that you can see the base. If you choose this to be the base, then the height would be drawn down to form that 90-degree angle at the base. Even if you start with a right triangle, you can still choose a different base and extend the height down to make another 90-degree angle. And this can be very, very useful if you're solving a complicated problem. The key takeaway is every triangle can have 3 different bases and 3 different heights. And it's up to you when you're solving a problem where you put the base and where you put the height. Let's focus our attention on right triangles. Remember, they all have 90-degree angles. And across from the 90-degree angle, we have a hypotenuse. We often call the base one leg and this height the other leg. We could also label right triangles as triangle A, B, C, where C is the hypotenuse, B is a leg, and A is a leg. We don't have to use A, B, C. I mean, we could use C, D, E. This side would be little e, this side little d, and this side little c. But we could also call this hypotenuse side CD. We could call this leg side ED, and we could call this leg side CE. And again, the order doesn't matter of the letters. And here we are at the Pythagorean Theorem, where a squared plus b squared equals c squared. If you remember, you may have proved this equation before. A square attached to this line, and a square attached here, and a square attached here, where you had a times a was a squared, right here, and b times b was b squared, and c times c was c squared, and you prove that these two areas were the same as this area. We can also label this triangle as triangle BAC or ABC or even CBA. It doesn't matter. Remember, C was the longest side of this triangle. Remember, the longest side is the hypotenuse, and you might find it useful to use the Pythagorean theorem written this way, where you have a length 1 and a length 2. Or you may find it useful to use the line segments in the formula, where the AC is the hypotenuse here, the longest side, and one leg is AB and the other leg is BC. That's fine too. One last concept here, and that is for any slope drawn on a graph, you could also form a right triangle. And I'll do that here. There it is. There's the right triangle. Across from the right angle is the slant or the slope of that line. And that may become useful when you're solving problems. Hopefully this little chit-chat helped review a few things you've learned about triangles in the past. We will need all of this information as we move forward in trigonometry. I want to leave you with a challenge. You may remember that the angles of a triangle add up to 180 degrees, but can you prove it?